Today we're going to talk about comparing quadratic and exponential functions. So let's get started with a warm-up. So it says, list these quantities in order from least to greatest without evaluating each expression. Be prepared to explain the reasoning. So with this, we're looking at 2 to the 10th, 10 squared, 2 to the 9th, and 9 squared. And so we need to do this without evaluating each expression, which means we shouldn't just be typing these into the calculator to figure out what they are. We're going to actually kind of reason through this a little bit. So what things do we know so far? If I'm looking at these, I know if we're going to go from least to greatest. Okay, one thing that we do know, or should know, is that 2 to the 9th has to be less than 2 to the 10th. Okay, because 2 to the 9th means that you're taking 2 multiplied by itself 9 times. And 2 to the 10th means that we're taking 2 and multiplying it by itself 10 times. So if we're multiplying it by 2 10 times, that's got to be more than multiplying 2 by itself 9 times. Another thing that we should know is that 9 squared has to be less than 10 squared. Okay? Just from your basic math facts from the past, you should know that 9 squared is 81 and 10 squared is 100. Again, I know that's kind of evaluating, but we're not typing it into the calculator to figure out. So now we have to figure out which order these go in. Is it going to be, 2 to the 9th, 2 to the 10th, and then 9 squared and 10 squared? Or is it going to be 9 squared, 10 squared, and then 2 to the 9th, 2 to the 10th? So let's actually look at what it means to be 2 to the 9th. So remember, that means that we have nine 2's there. Okay, so then here, if we're looking at kind of 4 of these, this would be 16 times 16 times 2. And that's telling us that we have 16 squared times 2 there. Well, if we've gotten to 16 squared, is that going to be more or less than 10 squared? Since 16 is a bigger base, a bigger number than 10, we know that 16 squared has to be bigger than 10 squared. So our least one would be 9 squared. The next one would be 10 squared. Then we would have 2 to the 9th. And last, the greatest one is 2 to the 10th. So here, these two are quadratic because they have an exponent of 2. Here, these two are exponential because based on what we've seen from our last unit, when they have the same base and you're taking things to an exponent, the variable's in the exponent, that means that it's an exponential. So here we're noticing that the quadratics are smaller than exponentials. Okay? So next up, we are going to look at some patterns here, and we want to figure out which one grows faster. So in pattern A, this one here, the length and the width of the rectangle grow by 1 small square from step to step. So if you're looking at this, the length is growing by 1 square each time, and so is the width. Okay? In pattern B, over here, the number of small squares doubles from each step to the next. So we started with 1 square, and then 2 squares, 4 squares, 8 squares, and that pattern would keep going. In each pattern, the number of small squares is a function of the step number n. Remember, to be a function, it means that the x's don't repeat, or the n's here don't repeat. So if we have step 2 with 1 block, we're not going to have step 2 again with some other number blocks as well. Alright, so with each of these patterns, we want to try and write an equation that represents the situation. We want to tell if the function is linear, quadratic, or exponential, and then we want to complete the table. And these 3 things can kind of be done in whatever order that you want. We're going to do the same thing for both of these. So we know that the length and the width grow by 1 small square each time for here. Maybe you don't know how to write an equation for that yet. So and we don't know if it's linear, quadratic, or exponential yet either. So let's look at our table. Okay. So We don't actually have a step 0, so we're going to get rid of this for both of these actually. So in the first step, maybe I can try to show lots at the same time. Okay, so in the first step on pattern A, there were no small squares. In step 1, in step 2 there's 1 small square. In step 3 there's 4. In step 4 there's 9. So how many do you think would be in step 5 if we kept going? So if we increase the length and the width by 1 square each, we would have a 4 by 4 or 16. Continuing on that, we would have 25, 36, and then 49 squares. Okay. Looking at pattern B, in the first step we had 1. In the second step we have 2 because we're doubling it each time. So in step 3 there would be 4. Then we would have 8, 16, 32, 64, and 128. So that's going to fill out the rest of our chart down here. Okay, so now let's see if we might be able to write an equation to go with this. So if we go back up here, this is 1 squared, 2 squared, 3 squared. It would continue on. Right? 1 squared, 2 squared, 3 squared. It continues on. And so how do we compare, well then this would technically be 0 squared. How do we compare this number that we're squaring to the step that's here? So the number that we're squaring is 1 less than the step that we're on. So here our equation would be, let's say f of n equals n minus 1 squared. Because on the 5th step, it would be 4 squared, and you would keep going. So whatever step you're on, you're taking 1 less than that and squaring it. So is that linear, quadratic, or exponential? Remember, linear means that it's going to be a line. Those are all in the form y equals mx plus b. If it's quadratic, it's going to have an exponent of 2. We've talked about that in the past. Exponential means that it has a variable in the exponent. So which one of those is this? It is quadratic. Okay, it's got that exponent of 2 there. So let's do the same thing over here. Here we're noticing that each time we're doubling this. Where have we seen that before where we double? Yeah, we've seen that with our exponentials. So that means that we're starting with 1, right? That's our starting amount, 1, we're looking up here, times, what are we doing each time? We're doubling. So it's going to be 2 to the, now it's not just n power, because that means that if I take 2 to the first power, there should be 2 blocks here. That's not what it is. But we're going 1 step back from that, okay? So f of x, I guess that should be f of n. F of n equals 1 times 2 to the n minus 1 power, or just 2 to the n minus 1 power. Now what is this? Is this linear, quadratic, or exponential? This one is exponential because the variable is in the exponent for this, okay? So down here at the bottom it does ask us how the two patterns compare if they continue to grow. So what things do you kind of notice with these? Well, each one they're getting bigger, right? Each time they're getting bigger. And with this also, do you notice that any of them have the exact same value? So here at 3 they have the same value, at 5 they have the same value. That's also something to notice. But if we're looking at comparing these things, the y values, so here each time we're doing what as we go down the table? So the exponential change is always 2. So as you go, all right, it's the exponential change is always, I guess we'll say, by a factor of 2 every single time that you go. To figure out the factor over here, well, even to figure out here, we would take 2 divided by 1, 4 divided by 2, 8 divided by 4, and you keep going, and you're going to get that same factor every single time. If we're looking here, well, we can't do 1 divided by 0, but 4 divided by 1 is 4. 9 divided by 4 is going to be less than 4, okay, that we just got here. 16 divided by 9 is going to be an even smaller fraction, and it's going to keep getting smaller and smaller and smaller. And as you're looking at these things, eventually your factor is going to be smaller than 2. So this one's always multiplying by a factor of 2. Here we're not always multiplying by that same factor of 2. We're multiplying by something different each time, and it's getting smaller and smaller as we go. So exponential change is always by a factor of 2. Quadratic change is by a different factor each time. Okay, so that's important to know as we go along. Okay? All right, let's take a look at 2 more functions. So we have p of x equals 6x squared and q of x equals 3 to the x power. And we're going to investigate the output of p and q for different values of x. For large enough values of x, one function will have a greater value than the other. Which function will have a greater value as x increases? So let's just start looking here first at these values. So if we evaluate, if we take this value and we substitute it in there for these things, so we would get 0, 6, 24, 54, 96, 150, and 216 if you evaluate that. So that should be 216. And on the q of x, if we take 3 to each of those powers, well, anything to the 0 power is 1, and then 3, 9, 27, 81, 243, and 729. Okay, and obviously those charts keep going from there, but that's what we're going to look at. So what do you notice here? Which ones are bigger? So here, q is bigger at 0. P is bigger in this space, right? All the way to here. At 5, q starts being bigger. And after that, q is going to continue to be bigger as well. Okay? So, which function will have a greater value as x increases? This one's going to keep getting bigger and bigger. That q of x, that exponential, is going to keep getting bigger and bigger as you go. So that is the one that is going to be bigger. Okay? Are you ready for more here? We'll look at just one piece. It says, Jada says that some exponential functions grow more slowly than a quadratic function f of x equals x squared as x increases. Do you agree with Jada? Explain your reasoning. So in everything that we've kind of looked at so far, the exponential will grow faster. Maybe not right away. There might be a space where the quadratic is going to be higher or growing faster, but there will also be parts where the exponential eventually will get bigger. Okay, in this case up here it was 5. At 5 or after 5, the exponential kept getting bigger. So Jada is saying that there are some exponential functions where the variable is in the exponent that grow more slowly than the quadratic function f of x equals x squared. Will that ever happen? Do we agree? Exponentials can be exponential growth or exponential decay. In this case, we've been looking at all exponential growth situations. Are there certain ones, though, that would decay? Well, of course there would be. So, yes, we agree with Jada. If we have, let's say, g of x equals 1/2 to the x power, it will decay. And if it decays, then it's obviously not growing faster. Okay? So in general, quadratics will grow more slowly than exponentials. Or I guess we could say exponentials will grow more faster, or will grow faster than a quadratic. And that's it.